So this video will cover three parts. First, I'm going to show brief introduction about matching network, how they look like, how they work. The second part, I'm going to show you how to use ADS software to design matching network. And finally, I'm going to show you how to design matching networks using Matlab code in case you don't have ADS. What is a matching network? Matching network is like a two-port circuit that maximize all the power coming from a source and deliver it to a load. And usually this does not happen if you connect the source directly to the load. So what does matching mean here? So matching here from circuit perspective means that the input impedance we see from the matching network is exactly the same as the source impedance. So in terms of scattering parameters, matching means that all the power waves that is incident on the circuit is absorbed, and which means that like there is no reflection that is coming back, which means that matching here means that S11 equals to 0. And if we assume that the matching network is lossless, so this means all the power that is absorbed by the matching network will go directly to the load, which means all the power coming from the source will go to the load. This is a practical example of using matching network in low noise amplifier. The amplifier here consists of two transistors with inductive degeneracy connected to the source. The input impedance we see from the gate here is capacitive, which means if we directly connect the source to the amplifier, most of the power will reflect back and the power gain will be 0. That's why we need like a matching network to transform this capacitive impedance into a real impedance. So this is one of the most common and basic matching networks that is used in circuits, which is using lumped components, and usually like the basic one is using two components, capacitors or inductors. And there are two like topologies for this matching network. The first one is using a series shunt component or using shunt series component. And as you see, the difference here is that here, from the source to the load, you start by a series component, then a parallel component, and here you start by a parallel component, then a series component. These components may be inductors or capacitors. So if you consider all the possibilities, you will find that you have 8 possibilities. The first 4 possibilities for series shunt when you have LC, LL, CL, and CC. So I wrote down here all the design equations that you need to know to calculate all the values for your circuit. So if you want to use these formulas, it's okay. Pause the video and take the formulas that you want. Here are the other combinations for shunt series where we have a shunt and a series component. So here I'm going to show you an example to show you how to apply this like formulas that I showed in the previous slides to calculate your matching network parameters. So let's assume we have a load impedance of 200 minus 100J and a Z0, which is a source impedance of 250 ohm, and we want to match them at 2 gigahertz. And let's assume that I want to use this matching network, which is a series L and shunt C. So let me show you how to use these formulas. First, we calculate the normalized admittance, which is Z0 over Z load, which is 0.2 plus 0.1 J. From these values, you find G, which is 0.2, which is the real part, and B, which is the imaginary part, which is 0.1. Then you directly substitute in these two equations to find L and C, and that's it. So easy, huh? Yeah, but wait a minute. Let's take another example. So let's take another example, but instead of matching to a loading impedance of 200 minus 100J, this time let's take 20 minus 100J. We follow the same procedure. We get the normalized admittance. We substitute here. We get the inductance. We substitute here to get the capacitance. But wait, we get like a negative capacitance. How come? Yeah, actually, this is like the important thing here is that like not all matching networks work for all values of the load. That's why you have to try different ones if they did not work for this kind of impedance float. If you are familiar of Smith chart, this may like save a lot of time to you. So here like the shaded region here are a forbidden regions, and the non-shaded ones are the allowed region where this matching network can work. For example, this circuit can work here on this white region, which means, for example, if we have an impedance here, it's gonna be like inductive and with real part greater than 50 ohm. For example, if we have like 100 plus 100J, yeah, this impedance can be matched using this one. So in this simulation example, we want to match a 50 ohm to a complex impedance, which is a 75 ohm and 0.5 picofarad. And this time we're going to use more complicated matching network, which is like a two-stage. And definitely this one, it is hard to use these relations discussed before. That's why we have to use like a simulation. And also one difference here is that this kind of matching network is used to make like a matching network for wideband frequency. So we'll start first by defining the unknowns or the variables that we want to optimize to be able to get the circuit parameters. So we use here from variable here, we define here, let's say CP1, which is the first parallel capacitor, and let's say we use 1, and CP2, and let's say L series 1, L series 2. Now we have four unknowns in our system, or four variables that we are going to optimize. Now let's draw our circuit. Let's start by a load. So we first define the simulation parameter, which is S parameter simulation. We define the frequency range from 1.9 to 0.1, and we choose, let's say, 1000 point. Then we define the goal of our optimization. We go to here, optimization. We define the goal here as dB of S of 1, because this is the scattering parameters, and we choose the scattering analysis that we already made. And here we choose the goal to be less than negative 15 dB. So I set a goal that like the scattering parameters over this range of frequency is less than 15 dB. And finally, I need to like let the ADS know that what parameters that I want to optimize, which are basically all of them. So from here, I choose opt and make the optimization here enabled. And I set the minimum as 0. Let's say 0.1 to 10. And I repeat the same procedure for all the variables. Okay, now I have all my variables are ready for optimization. It only remains like to choose a goal, to choose the optimization. So here I'm gonna like put 1000 iteration using random optimization, and here choose all variables. That's it. I think like errors should be db. Now it only remains like to press optimization. Okay, now we have a result where it shows like a matching over the bandwidth, which is showing like S11 less than -15. So in this part, guys, I'm going to learn you how to make your own matching network using Matlab, and how to make it like customized, such as like you may like find your own matching network. So I first like, since I'm going to use optimization, I'm going first to define my cost function, which is something like my goal function. I first make a new function, and I'm going to call it my cost function. And the input variables to this my cost function will be first the parameters that I want to optimize, and let's say Z0, which is a characteristic impedance that I want to match this circuit to, and finally will be the frequency range. And the output will be, let's say, error, which this error gonna tell you how far you are from your goal. And let's say here we have also S goal. So now let's define like our circuit parameters as CP1 as the first element of the parameters of the vector parameter, CP2, and let's say L series 1, L series 2, and let's say this is 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay. So we calculate the impedance of each like components as dB1 equal 1 over J omega CP1, and we define omega here as 2 pi frequency, and we put a dot here so that we calculate it in terms of vectors. And we repeat this procedure for ZB2, Z series 1, and Z series 2. So now we have all the impedances. Okay, now to calculate like the S11, we're gonna start from here, from the load, and we calculate the effective impedance here, which is a series of this one plus this one. And then we take the parallel components and the series component until we get the equivalent input impedance here, and then finally get S11. So to do so, we first like should define the R load and C load here, which should be the input to the function, and here we define Z load as R load plus 1 over J omega C load. Now let's calculate Z temp as Z load. So it should be Z load plus Z series 2. And this T temp should be taken in parallel with Z parallel 2. So this is like I'm calculating the parallel equivalent. Now I'm here. So let's do it one more time. But this time it's gonna be Z series 1 and z temp, and finally we take z temp with z parallel 1. That's it. And finally z input equivalent is z underscore temp. Now to get S11, S11 is defined as z input equivalent minus z0 over z input equivalent plus z0. And we're gonna define our error as absolute of S11 minus S11 underscore goal. So we wanna like this S11 to be less than S11 goal. That's why we need like to set all the points that are less than our goal to 0. And this can be simply done as error of error less than 0 equals 0. And finally, since error here is a vector, we can return like the mean of it. Because at the end of the day, the error should be single value. That's it. Finally, guys, after making our cost function, we just need to make a main where we define the R load, the C load, and the frequency range, and the S goal. And here we define just an initial condition for the optimizer to start from, and this will be the line that will make the optimization, where we call the function fSearchMean, which is a built-in function in Matlab, where it minimizes the goal. And if we run this, we will find that like we have a good matching in the required frequency range.